Hey, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
Houston, we don't have a problem. Today we want to talk about kinetic energy. That's the energy of motion. If you recall, we've been having a conversation. I can't talk. And energy, all of energy, is actually it's the sum of all the types of energy. The energy of a system would be K, kinetic energy, plus gravitational energy, spring energy, thermal energy, chemical energy, nuclear energy, there's et cetera, et cetera, et cetera. But today we want to focus on kinetic energy. So we talk about kinetic energy. Let's talk about what it is. And the best way to understand this is, now kinetic energy is the energy when something is in motion. But I want to connect this with things we've learned before. So let's think about a car, okay? We've got a car, bad car. Okay, and if we apply a force to that car, we've learned from before, we can move it. So we've got the car at two different moments in time. He's got a V1 and he's got a V2, right? If you add some force to the car. And if you apply a force to the car, it's going to travel some distance. So if we ask the question that we've already been asking, how much work is done on the car, as you recall, work is equal to the force times the distance. But if you also recall, if we go back to our understanding of kinematics, we have an equation, if you recall, V2 squared equals V1 squared plus 2a delta x. Now, the d and the delta x are the same. And then the a, if you recall from the last unit, a is the force divided by the mass. So if I were to plug in and rewrite this, V2 squared equals V1 squared plus 2 times the force over the mass, that's the A, times D. I'm substituting D in for here. What we could do is we could solve, now actually back up, and if we know that work, where did I put that? Work is force times distance, and there we have force times distance. So we could rewrite this equation. We can say V2 squared equals V1 squared plus 2 times W over M. All right, and that work, though, because this is the energy of the motion, so what we could actually do is not put a W there, is we could do a K. This is the energy of something in motion. Now, I'm going to simplify this, but if you simplify this equation, what you get is you get that the kinetic energy, or K, is equal to 1/2 times M times V, is it V2? Yeah. V2 minus V1 squared. Or we could say K1, the initial state, is equal to 1/2 mv1 squared, and K2 is 1/2 mv2 squared. And this is really the big equation. Basically, kinetic energy is 1/2 mv squared. It's really the change, though. It's the change in the velocity. So if you change the velocity of an object, then what's going to happen is you're going to get more kinetic energy. And because when you plot, so let's sketch this, if you're to plot kinetic energy as a function of the velocity, it's going to be a curve like this. It's a exponential curve. It's an exponential function. And when that's the case, that means if I were, and there's actually some important implications. Let's say that I'm going 1 mile per hour, or let's say 10 meters per second. And then I double my speed. So have I doubled my energy? Well, if you go back to our equation, the mass of the car, I'm in a car or something like that, isn't going to change, and half is still half. So if this is at 10, 10 squared is 100, right? So that'd be 100 would be the factor when you do 10 squared, but when you do 20 squared, that's 400. So if you double your speed, you do not double your energy, you quadruple, since it's to the square. If I were to triple, it'll be 9 times more energy. That is actually one of the big reasons why when you're in a car accident, how fast you're going makes all the difference in the world. If you're doubling your speed over what used to be, you're not doubling your energy, you're quadrupling your energy, quadrupling the opportunity for a bad thing to happen to you or to your car or what have it. So let's do a problem. We get this in the History Center. We've got an old canal boat pulled by 2 draft horses. I've actually been on some of these canals riding bikes, and they're pretty cool places. And so I've got a boat, and we know its mass, so M equals 55,000. And it starts at a V1 of 0, got that? And there's a drag force, so we have a force, and they give us the force to be, so F equals, what is it, 1,400 newtons. And V1 is 0, but it gets to a final speed of V2 of 0.70 meters per second. And they ask you to solve for the distance. How far, if you did V2, et cetera, et cetera. Now this is actually, sometimes it's like where you're mixing up our 2 different equations. If you remember, work is force times distance. You're solving for distance. But also, we really realize that if something has moved, that's also equal to 1/2 mv squared. We're solving for distance. And guess what? We know everything here. So what's our force? Our force is, I'll say 1,400 times d equals 1/2 times 55,000 kilograms times your velocity. It's actually the change in velocity, right? This is, see, the change in velocity went from 0 to 0.7, so that's just 0.7 squared. And I'm not going to belabor this, but you can do some algebra and you can solve this question, and I get a d to be 9.63 meters. So this is going to be very common when you're looking at these questions, that you could have something like this, where you're going to compare the work, force times distance, because say, wait, work is force times distance, and kinetic energy is 1/2 mv squared. They don't work. But remember, in the earlier part of this video, I showed how work comes, or this equation comes from the work equation and our understanding of kinematics. So the reality is they're really measuring the same thing, but this has to do with something that's moving, and work by definition is always force times distance, but they're related, and then it's simple math. So Houston, I don't think we're going to have a problem with this section. Kinetic energy is one of those easier concepts to comprehend. So yeah, we'll see you in class.